a new area that's come up in the last really 5 years in EEG analysis, known as wavelet coherence. So we've talked about coherence and we've talked about wavelet analysis. So the next sort of logical jump is to talk about wavelet coherence. It's basically the same thing as frequency coherence, only it's done, rather than doing it as a cross spectrum, we're actually doing the cross spectrum or the autocorrelation between on the wavelet transforms. So because of the nature of the wavelet transform, you saw in the previous lecture that we had some 20-odd scales. Each wavelet transform has its own frequency characteristics, and so out of then the wavelet coherence, you'll get coherence value for each scale. So we get a lot more data out of wavelet coherence because we typically have to use a lot more scales. Here's the mathematics. This basically is what's analogous to the wavelet cross spectrum, where this W is our wavelet transform, X of U would be our original data, psi would be our weighted and scaled wavelet function, or our wavelet function. So the wavelet transform comes out, and so now you can see you have channel X, channel Y, and you're just basically doing the same kind of integral that you did on the for the frequency coherence, except in this case, clearly you're not taking a Fourier transform. So whereas previously we had the cross correlation, and we took the Fourier transform of the cross correlation to get the function, here we're just taking the cross product of the X and Y channels wavelet transform data. And so once again, to get the wavelet coherence, exactly the same form that we used for frequency coherence, just got the wavelet function instead of the function in the frequency domain. Not going to talk a whole lot about wavelet coherence. Here's the issue with wavelet coherence. It's very difficult. A lot of people publish these papers and they have these beautiful pictures. Here's my wavelet coherence map of situation A and situation B, and then they draw these conclusions about how they look different. But it tends to be very qualitative. So really, I'm not comfortable, and I think a lot of people aren't comfortable, that there's a good specific feature defined that has of a quantitative nature for wavelet coherence. And people have investigated this. We have investigated it a little bit in my lab. Still not really happy that we have great numbers that we can use that make us happy, that we can say this is our wavelet coherence feature. So unlike frequency coherence, where you can take an average across the frequency band, wavelet coherence just a little more complicated. You can certainly take an average of wavelet coherence across the scale. The problem is that what you gain from doing a wavelet is temporal resolution. And so obviously as soon as you average across the wavelet at a given scale, you have gotten rid of your temporal resolution. So you sort of defeated the whole purpose of using a wavelet. Maybe and maybe not, just depending on how you interpret it. So anyway, that's the story on wavelet coherence. It's still very much a research topic, still very much something that people are looking at. It was actually developed for looking at long-term weather patterns. So it's still an active area of research. The only other parameter that we really haven't mentioned is correlation. Correlation is not used a lot as a connectivity measure between EEG channels, and the reason is they just usually aren't well correlated. And if they are correlated, it's usually because there is some artifactual or noise signal, characteristic noise signal, like the pickup of 60 hertz noise that's superimposed on the EEG. And so when you get high correlations, you're often seeing correlation between not the EEG but something else that is a part of your data. But this would be how you would calculate the correlation between EEG channels. People are revisiting correlation as they look at graph theory models, and also as they look at sort of these models of structural equation modeling and that sort of thing. So there are some sort of revisiting of correlation in more modern techniques as sort of a preliminary step to analysis, but you normally don't find this mentioned in the literature a lot. There are some additional parameters. One is phase synchrony, has been used quite a lot to replace coherence, frequency coherence, or to augment frequency coherence. Giving you a reference to a paper as a part of the course that really summarizes a number of different connectivity techniques and looks at how accurate each one was at classifying a pretty well-defined classification problem. So that's part of the reading assignment and really should supplement this series of lectures in different EEG parameters and connectivity measures. So the last few sets of lectures have given you a little bit of an overview of what are some of the parameters that people look at and publish. You notice that we haven't done any kind of source localization. We haven't done any kind of neural modeling. That's fairly common. So, for those of you who are really stressed that there's all this really complicated neuroscience and engineering and physics that go into making these models to understand EEG data, just be informed that there's an awful lot that you can do in analyzing the EEG and using it as a biomarker without even trying to do any source localization or dipole fitting. So while intellectually that's a really interesting field of research and certainly one that we don't want to ignore and one that we want to pursue, just be advised for simple EEG analysis problems where you have a cognitive state or a disease state that you're trying to identify in like a pattern recognition or a diagnostic application, that there's a lot you can do with the EEG without the higher level sophisticated modeling that they talk about a lot in the some of the short courses and some of the published literature. So this concludes then this little series of lectures on EEG analysis techniques.